Today we're going to talk about colligative properties. This starts in your textbook. I've got my textbook here. I'm shuffling through some of the pages, but this starts kind of the, there's 4 sections. There's actually a section 12D. We're not going to talk about that. So today we're going to talk about the last section that we will discuss as a class from chapter 12. So that is 12C on colligative properties. I'm going to, let's see, let me pull up my presentation here. So the colligative properties, what are those? Well, let's talk about that. So the colligative properties are properties of a solution that depend only on the number of solute particles present. So when we look at these ideas, what we're going to look at is what happens to the solute and what effect does it have on the solvent that you're placing it in. There are going to be 3 things that we talk about. 2 types of, broadly, 2 types of problems, but 3 kind of characteristics. We're going to look at vapor pressure depression, which means lowering the vapor pressure. And then we're going to talk today about boiling point elevation. So if you lower the vapor pressure, you have to increase the temperature to get that substance to boil. So they're related in that sense. So let's go ahead quickly and talk about vapor pressure. Actually, before we talk about vapor pressure depression, I want you to make sure that you watch this 2-minute video of not me, of the other gentleman talking about vapor pressure, just to make sure you understand it. I will try to draw a little bit a similar example to what he did just to reiterate it, but I would, let me pull off my presentation for just a second. I want you to understand vapor pressure. It's not complicated, but I want to make sure you understand it because otherwise everything else we talk about doesn't really make sense. So let me lower this a little bit so you can see my whiteboard. And I was playing with it a little bit earlier. That's why I need to erase it. So here, I'm going to draw a beaker. I'm going to put some water in my beaker. And then I'm going to put a lid on my beaker. Humor me. All right, so there's my lid. All right, no water can escape. But there is some space between my water line and the surface of my lid. Okay, so you guys know about the water cycle. You've had that since elementary school, but you have water, it evaporates, it becomes gas, water vapor. It goes and forms clouds, and those clouds get heavy, and water falls back to the earth in the form of rain. And sometimes, not this year, we get snow or ice or sleet. All right, sometimes hail in the summer. Well, what you're doing basically with this situation is you're creating a mini water cycle. So you've got water here, and water, all these water molecules, I'm going to draw them as little circles, but you know they're not really just little circles, but for time's sake, here are the circles. Okay. Those are all on the surface, and then there are all those other water molecules down here. But these are the ones on the surface. And what happens is the ones on the surface generate enough energy that eventually they start to pop off into the air, the space above that, and become water vapor. And so this happens. And you have all of these water vapor molecules above the surface of the rest of your liquid water. So here is the vapor. And then down here is the liquid. At some point, though, just like when we get rain, because the clouds have gotten saturated, at some point, this area, the vapor area, becomes full, and the water has to start dropping back. And that's what happens. You get this water molecule actually falls back down, and this water molecule falls back down. But at some point, you reach what's called a dynamic equilibrium, where you have the same number of water molecules as vapor. That number remains constant. as does the number of liquid water molecules. That remains constant too. That's considered the dynamic equilibrium. Now, the whole idea here is that in this kind of container, a sealed off container, you have a certain number of water molecules that remain a vapor. Well, that's a gas, right? And gases exert pressure. So there is a vapor pressure value for this little setup that I've drawn here, not very artfully, but hopefully you will understand that this is the water vapor and there's a certain amount of pressure up there. Now, how does changing this from pure water to, say, salt water, how does that affect the vapor pressure? Well, let's go back to my slides and spend a couple of minutes on that. So here's the idea. If you were to put a solute that is less volatile, and what I mean by that is less likely to become a gas than the solvent it's in, which in most cases that's the situation. Sodium chloride, that definitely is. Sodium chloride is very unlikely to become a gas as compared to water. So if you add sodium chloride to water, let's do that. I'm going to go back out here and let's pretend that instead of having pure water in our beaker, we have water, but also we have some sodium and some chloride ions. And what happens is before we had salt in our water and it was just pure water, every molecule at the surface was water. But that doesn't happen when you have a solution, because you have some of this area, some of this water is actually salt and water mixed together. And so these sodium ions and get near the surface, and so do those chloride ions. And they kind of kick the water molecules out of the way. Well, if there aren't as many water molecules on the surface, because they're being shared space with sodium and chloride, you're not going to have as many water molecules becoming vapor. So if you have fewer water molecules, you have less vapor pressure. Fewer water vapor molecules, lower water pressure. All right, so that's basically what I'm saying down here. The fewer water molecules you have at the surface, the fewer water vapor molecules you can have, because they can't escape the surface and pop off into the vapor area. And so you have fewer molecules, lower pressure, okay? Now, a couple of things to keep in mind, and this is going to follow us through with these types of problems, is that the type of molecule that you use for a solute affects how much the vapor pressure is lowered or depressed. So when we have sodium chloride, that dissociates into sodium ions and chloride ions. So you actually get, for every 1 mole of sodium chloride crystals that you put into your solution or to water, in the solution, you get 2 moles of ions. If you do magnesium chloride, which dissociates into 1 mole of magnesium right here and 2 moles of chloride, you actually get 3 moles of ions in the water. And then if you go to aluminum chloride, you get 3 moles of chloride ions, and 1 mole of aluminum ions. And so you actually get 4 moles of those ions that dissociate in water. And the way that works is if you have more and more ions occupying, say, your water in your solution, then you're going to have fewer and fewer water molecules on the surface, because it's having to share a lot more space with those ions that have dissociated. So the fewer water molecules that you have on the surface, the fewer water molecules that become water vapor, and the lower the pressure that those fewer water vapor molecules make. Okay, so adding solute lowers the vapor pressure, and the more moles you have through the dissociation process, the more moles of ions, the lower or the greater the effect of the depression is. Now, let's look at this. Boiling point elevation. Well, boiling point is the point at which a liquid becomes vapor. All right. So if you lower the vapor pressure because you've added solute, it's going to require higher temperatures to raise the vapor pressure enough to get your substance to essentially boil, to get molecules to evaporate and become vapor. So we're going to look at a couple of formulas. This is just a change formula, which it probably makes sense, even though we use Greek symbols and subscripts to make it look fancier than what it really is. But delta, this is a Greek letter, looks like a triangle, I know, it's a Greek letter delta. That is used, I think we've discussed this before, but it's used to signify a change in something. So a change in boiling point takes the boiling point of the new substance and you subtract it from the original substance. Do you have to memorize boiling points of substances? No, they'll either be given to you or there's a chart that would get you that gets us started on page. Let's see which page was that. Yes, 322 in your textbook. We're going to refer to that chart. So no, you don't have to memorize boiling points, although you should probably know just because it's water that at normal situations, the boiling point of water is 100 degrees Celsius. Then there's this thing that's going to be called a constant, a molal boiling point constant. Now, keep in mind, did you just see that? Molal. So that's what we're actually going to be using. We're not going to be using molarity in these calculations. We're going to be using molality. So 1 mole of particles in 1 kilogram of water elevates the boiling point of water by 0.512 degrees Celsius. Notice 1 mole particles or solute divided by mass in kilograms of solvent, that's molality. So there's going to be a molal boiling point constant for many of these substances that we talk about. You do not have to memorize those constants either. They're also, several of them are located on page 322 in this chart. Okay. I know that's not real clear through the camera, but you have your textbooks that you'll be able to use. There's also another formula that will help us calculate the change in temperature. You're going to take that constant that you can look up in a chart, or it'll be given to you to solve the problem, and multiply it by the molality. So some of these problems will require you to solve for the molality before you can actually figure out the new boiling point. Now, again, this is a change in boiling point. It is not the new boiling point. So many times after you solve for this change in boiling point, you have to add it back to the original boiling point. So ionic, we actually talked about this already. I just want to reiterate it. Ionic solutes produce more particles in solution than covalent compounds do. And we're going to talk about particle molality, but we've actually already done that back in this slide. The whole idea is that you get more moles of ionic compounds because they dissociate into their separate ions. So sometimes you're going to, in these problems, you'll solve for molality of the solution, but then you actually have to multiply it by a factor of 2 or 3 or 4 even, depending on the ionic compound that dissociated, because you actually need to get the particle molality as opposed to the molality of the entire thing. I'll show you what that means in one of these problems. There's an example of that. So let's start with one problem where it's not ionic. We have acetone, which is fingernail polish remover. And we want to know the boiling point when you add a solvent to it. And the solvent we're going to add is naphthalene. And we're going to add 1/2 mole to 1 kilogram of acetone. Well, we don't have molality, but it's given to us in the problem because we already know the moles, 0.5 moles, and we know the mass already in kilograms of acetone. Of acetone. So we know that we have 0.5 moles of naphthalene, that's our solute. We know that we have 1 kilogram of acetone, that's our solvent. So the molality calculation here is actually really easy because it's just 0.5 divided by 1. So 0.5 molal right there. And we can look up our constant, or it's given to us here actually, 1.71, but that would be in the table that I referred you to in your book. So the constant for acetone is 1.71 degrees Celsius per molal. And then we're going to multiply that by the molality, which is 0.5. and you get 0.855 degrees Celsius. But notice that's a change in boiling point. That is not the boiling point, but I'm asking you for the boiling point. So what you do is you take this change and you look up in that table on page 322, you look up the boiling point of acetone, which is normally 56.2 degrees Celsius. So I add 56.2 degrees Celsius plus 0.855 degrees Celsius, and that gives me 57.1 degrees Celsius. So the new boiling point is about 0.9 degrees higher than the original. So that's how much it elevates, by 0.9 degrees Celsius. Now, this next problem that we're going to talk about deals with that particle molality concept. So let's look at that closely. I'm going to use magnesium chloride as our example because that dissociates into 1 magnesium ion and 2 chloride ions. So keeping that in mind, let's read the problem. If 425 grams of magnesium chloride are added to 675 grams of water, what is the boiling point of this solution? All right. Well, the first thing I've got to do is figure out the molality, because then I can use that delta T sub B equals K sub B times the molality. All right. Well, the molality, I have to find the mass in kilograms of water. I have it in grams, so I'm going to divide that by 1,000 and get 0.675 kilograms of water. Not too bad. But I don't have moles, I have grams of magnesium chloride, so I need to divide by the molar mass, and I get 4.46 moles of magnesium chloride. To get the molality, I divide 4.46 moles divided by the mass in kilograms of my solvent, water, and I get 6.61 molal magnesium chloride. Well, that's great. But that's magnesium chloride, not magnesium ions and chloride ions. So what I actually have to do, because of that particle molality situation, keep in mind that there are 3 particles to factor into the problem. 1 magnesium ion, 2 chloride ions. So the molality that I have to use in my problem is 6.61 times 3, or 19.8 molal. That's what I have to use in my delta T sub B calculation. All right. So now that I have my molarity and it's my particle molality, actually not molarity, but now that I have my molality and it's the particle molality, I fill into my formula. K sub B, which I look up on the table for water, 0.512. My molality based on the number of particles in the water, 19.8. And I get 10.1 degrees Celsius. That's my change. I remember probably, but if I don't, I look it up, that the boiling point normally of water is 100 degrees Celsius. And so I add 10.1 degrees Celsius to that. And I get 110.1 degrees Celsius. That's the new boiling point once I've added all this magnesium chloride to the solution. Okay. Then there are going to be problems where you work backwards. This time I'm not solving for the boiling point. I'm solving for the molality of the solution. Right? So if I solve for the molality of the solution, I can still use that formula, but I have to rearrange it. So if I go back to this formula, I rearrange it and determine that molality is equal to the change in the temperature divided by that constant that I can look up. And I've been given the 0.4 degrees as my delta T sub B. Now, I'm going to stop for a second and I want you to think, is this what I use? Okay, I'm going to tell you that no, it's not what I use, because NaCl associates to sodium and chlorine, so 2 moles. All right. So I'm going to cut that value in half. I'm not going to use 0.4 degrees Celsius. I'm going to half that. I'm going to use 0.2 degrees Celsius. So I'm going to take the change of temperature, which is 0.2 degrees Celsius, because I'm taking into account that it was doubled because of the 2 ions. So for sodium chloride, it's only going to be 0.2 degrees Celsius. And then I'm going to divide it by the water case of B, which again, you can look up. It's 0.512. So I get a 0.391 molal solution. Now, another type of problem that you could do from this is you could take this one step further, and you could say, okay, well, I've got 0.391 molal solution. Okay, and then you could take from that, you could be asked to perhaps figure out, if you're given slightly more information, the number of grams that you dissolved. We can't really know all of that here because we don't know how much solution is in there. Okay, but if you know the molality of something and you know the amount in mass of the water, of the solvent, then you can also find out how many grams of sodium chloride you needed to make that solution. All right, I'm going to stop with my lecture for today there. Now, I am going to come back and see you guys for a second, because what I want to do really quick is show you the assignment that's on Google Classroom. Make sure you understand what you're supposed to do. So let me pull up my Google Classroom for a second, and then I'm going to share that with you as well so we can just talk about it a little bit. It's not complicated. I just want to, Mercy, I hope I'm clear in the assignment. Of course, you can always hop on during office hours or send me an email if I'm not perfectly clear. You will not see this assignment yet. Just know that it's coming. Now, let me share it with you as we discussed. And look over here. All right, I'm hoping you can see. All right, so your assignment for today is, hopefully you've done this. Watch the vapor pressure video. You are currently watching my video. Then there's no attachment today. There's no worksheet set. You're going to do problems from your book. You're going to answer questions on page 1, 2, 3, or excuse me, on page 327, 1, 2, 3, and 5. Okay. Then you're going to go to page 333, which is the end of the chapter. And I want you to answer question 22. There are 2 parts to it. You choose, there's the list of 4, and you choose the highest or something. And you'll see the directions, but there's it's 2 parts, but you're just choosing the correct answer. And then I want you to turn to the next page and answer question number 24. Let me, for clarity's sake, I'm sorry, I'm flipping to my book. I want to put the page number there so no one's confused, but it's actually page 334. So let me edit that just a little bit. Okay, now there are 2 parts to this, B and C. For part B, it's going to give you some information. Don't panic. Remember that 1 gram of water is equal to 1 milliliter of water. Therefore, 100 grams of water is equal to 100 milliliters of water, and 1,000 grams of water is equal to 1,000 milliliters of water, or 1 liter. All right, so keep that in mind for the molality problem. Okay. Oh, and then this is a big typo too. My goodness. All right. And then for part C, so you got part B, keeping this conversion factor in mind. And then part C, remember 1 mole of NaCl will dissociate into 2 moles of ions. Now, hear me out for just a second, guys, before I close. I think this is going to be a little harder for you. Try these problems. They're not due until Wednesday at 1:25. Okay, so you have office hours Wednesday morning. Please check in Wednesday morning if you are confused. I can use my whiteboard to the best of my ability. We can chat about this. I want to help you through them because you do need to know how to do these. I'm not going to give you a ton of problems, as you can see. Some of these aren't even like calculations. Only a few of them are. But please check in office hours if you aren't sure about how to do them. Okay. All right. I am going to sign off now. I hope to hear from you guys soon. Let me know if you have any questions. I'd love to talk to you during office hours. I'm missing you guys a whole lot. I will check you later.